and I will give the word to Elko.
Okay, well, welcome. I've shared my screen, I think. You're seeing this?
Yes, yes.
Good, good, good. So this is all about ALMA simulations with CASA. iTrain number 15. You have already done the OST, Observing Support Tool, as iTrain number 5. So this is sort of a follow-up on that. And I'll touch up a bit on the OST again, but then move on to CASA later.
Elko, sorry to interrupt you, but it's not the full screen mode currently.
No, I know, but that's
Okay.
that's on purpose. So
Okay.
I made doing this. I want to be a little bit interactive, so I've got my windows here to
Okay,
show you
good.
stuff. I hope this is big enough. If not, then I can make it full screen. But
I think it's good. Thank you.
it's good, right? Okay, good. So the first thing we should ask ourselves is, why do we actually want to do ALMA simulations? So what's the use case here? So the original use case for simulations was to make predictions for ALMA proposals, especially in the early cycles, where you had to prove that you could actually achieve your science aims with the relatively low number of antennas available at the time. So early science was like with 8 or 10 antennas, which meant that the UV coverage wasn't optimal. And then simulations were often used to prove that you could still do whatever you wanted to do. So this is less the case, of course. Now we have lots of antennas, but still you can use the simulator to make quantitative predictions for your proposals to see whether you can actually do things and test whether you're not resolving out flux or anything like that. So the effects of missing spacings, recovering structures, surface density, brightness, all that kind of stuff you can check. Now, once you have your ALMA data, or once you're using someone else's archive data, you can compare the data to models you might have. So this is more of an interpretation of any ALMA data you have or you got from the archive. So that's the more traditional role of the simulator, I guess. There's some other use cases here. I'm personally using it, for example, to test source finders. So you can make predictions, for example, galaxies in a cosmological field. You can see whether ALMA can actually find these again. And you use large numbers of mocks for that. So this is using the simulator in batch mode for large quantities. Another interesting use of the ALMA simulator, or actually the CASA simulator, I should say, is to compare ALMA mocks with what might be possible with other telescopes. The CASA simulator doesn't just do ALMA, it also does the VLA, Meerkat, VLBI, and all kinds of other telescopes. So this is also useful. And we actually put out a paper on ATLAS, the future single-dish telescope, where we try to compare what ALMA can do and what a large single-dish telescope can do, and we use the ALMA simulator for that. So there's lots of uses for this. The original use was just to see whether things could be actually observed. So this is a protoplanetary disk in band 9, and we compared what you could do with early science and what you could do with the full array. So this was an early use of the simulator. The same with nearby galaxies. Can we actually resolve things? Can we still see stuff? So you can see in the early science image on the top right that all this lovely structure in the spiral arms just gets blurred. And you really need the full array to see the whole thing in the bottom right image. So here the simulator is fairly useful to see what you actually need. Now, of course, which ALMA simulator are we talking about? Which ALMA simulator should you use? People who use CASA and know CASA relatively well, for these people, it's probably best to use SimObserve, which is the CASA task to simulate. But of course, ALMA is also catering to people who haven't done any radio astronomy or interferometry in the past and are not CASA users. People who usually do optical astronomy or infrared astronomy. And for them, there's the OST, which is a web tool that's sort of a graphical interface between the simulator and the user. This was already covered in an earlier iTrain session. So a bit more specifics, SimObserve and SimALMA are CASA tasks, which are used to produce mock ALMA data. But the main work under the hood is done by a tool, the actual simulate tool or SM tool. So the SimObserve task, which is actually Python script, is just a user-friendly interface to this toolkit. And SimAnalyze is an extra task to do plotting and analysis of the mock you actually produced. It basically runs clean and does lots of plotting to see how good the model is. And SimAlma was a more recent development that's actually doing everything in one go, but can also combine 12 meter, 7 meter, and total power mocks. And it just relies on SimObserve and SimAnalyze, so it sits on top of that. But this is for CASA users, and of course we're going to talk about these mostly here. And the OST is a web tool that uses actually the same SM tool underneath the hood that SimObserve uses, but it's a bit more simplified and not quite the same, which also means that the results are almost but not quite the same. I'll get into that a bit later. So SimAlma, which is probably the easiest to use, it literally simulates what ALMA can do. It can simulate an ALMA observation using the 12 meter, 7 meter, and total power arrays, or just one of them. You can put in a model image, or you can put in a list of components, so point sources, for example, and a particular configuration of ALMA antennas. Of course, for the 7 meter, that's always the same. But for the 12 meter, we have varying configurations. And the output of SimAlma is a measurement set, which is useful because then CASA has all the tools to actually look at that and analyze your model. But you can also generate images from that, and you can then turn those into FITS files as well. That's quite useful for your proposal, of course, because you want to show some image in your proposal. So as I said, SimAlma uses SimObserve and SimAnalyze, and it runs that as many times as possible, or as necessary, sorry, to put it all together. So it runs it first on the 12 meter array, then the 7 meter array, and then the total power array, and then combines it all. This combination can be done in several ways. You can also do this manually yourself if you want to try something else. I mean, this is, of course, a bit of a black art, how you combine 12 meter, 7 meter, and total power data, and there's various ways of doing it. There's a warning here, but it's just a technicality that SimAlma should not be run multiple times on the same project. Because it might override all the results, and SimObserve, SimAnalyze don't. So this is just a warning. Okay, let's get into the specifics. I'm going to bore you now with the default parameters for the SimObserve task. I'm not going to read all these, but what you should just do is start up CASA, type in task name is SimObserve, and then int, and you can see all the parameters. And then you can change those, set them to whatever you want, and type go, and that's how you run the simulator interactively. That's not the easiest way of doing things, of course, because you need to type in all these parameters. So I'll get to how we can do things more quickly later on, but this is just for reference. These are all the current parameters. This is for SimAnalyze, which basically runs clean, so a lot of clean parameters are in there. And so that's the first part. In the image part, these are basically the clean parameters, and then the analyze part is just what it should actually plot. And SimAlma is a bit of both, so it's more restricted, but this is probably best for beginners. You still put in your sky model and your pointings and all that, and how you want to image it and the graphics. So it's a combination of SimObserve and SimAnalyze. But we'll get into that in more detail later on as well. So how do you run SimObserve? So the easiest way, or the most straightforward way, will be in CASA to just type in SimObserve. You see all the input parameters. You change them as desired, and then go. And whatever you put in, the parameter settings will then be saved in this file simobserve.last. So you don't need to do it again later on. You can just read that again in the next session using the CASA command tget. So with tget, you can read simobserve.last and then do it again. So this is starting from scratch and doing things manually. Another option is to copy the input parameters, all of them, from imp into another file. Or you just copy simobserve.last to another file and edit that file. So this gives you all the parameters you want. This you can then read again using exec file, that file name. And you can even add go at the end. So doing exec file mysim.py actually runs the simulation straight away. It's probably best to also add task name as simobserve at the beginning, just to make sure that you're actually doing simobserve, or something like defaults simobserve. I'm saying the same things twice here, so the last bit should be removed. But the same applies, of course, to sim analysis in ALMA as well. Now, this is one option. Another option is, and that might actually be useful, is to use the OST for this. The OST itself is aimed at novice users or users who haven't used CASA before. And it's just a nice graphical interface to produce simulations. And it gives you an image at the end, which you can then plug straight into your proposal. And this has been running for many years now. We're now version 9, I think. And it's a really advanced tool and working well. So here's the web address. So it's also based on the SM tool, just like simobserve, but there's slight differences there. So if you run both simulators on the same input set, you get slightly different results, especially in noise properties. So it's not too bad, as you can see. And if you do this, if you make the comparison quantitatively, then it's doing fairly well for the lower frequencies. So this is a comparison of the OST, the red dots, with 2 settings for simobserve, the green square and the blue diamond. So for the lower frequencies, so band 2 to say 8 or 7, there's hardly any difference. But for the high frequencies, there is some difference in the noise properties. So this was done using an empty map. So no actual source in there, just a pure noise map. So this is something to keep in mind. So this is the OST. This is how it looks like now. It's just point and click, and you can choose your instruments. You can take something from the library, an input image, or upload the FITS file yourself. The FITS file has to have some properties. I'll get back to that later as well. So the FITS file needs some keywords in there, otherwise it won't run. But you put all these parameters in there. You can do this yourself, or you can look at the iTrain number 5 session again, how this works. But the best part is that at the end, when you get the actual image, you also get 3 files you can download for use with CASA sim data. Sim data is the old name for the ALMA simulator. It's now called simobserve, but it used to be called sim data. That's still here. What it gives you is the input sky model, which is slightly processed, because you can rescale your sky model, or you can smooth it a bit, or the OST already does stuff to your input FITS format, to your FITS file, and you can download that again. Then it gives you the simdata.last file. This is a file containing all the parameters that simobserve needs to run, and sim analyze as well. And it gives you a pointings file, so the pointings that were produced by the OST. The latter one you could, in principle, ignore and use your own pointings for simobserve, but it gives all these. And then what it actually gives you is this file. So you already see all the various parameters here. And you simply use this as input to simobserve. The sky model here is the file that you also need to download. And this is the pointings file that you can download. You can see that here set pointing is set to false. If you set this to true, it will ignore the pointings used by the OST, and you can try other pointings. But here it just does exactly the same as the OST is done. This might be or might not be convenient. And all the parameters are set automatically. So this is a good starting point. It does the same for SimAnalyze. It also gives you all these parameters. It gives you the project name and all the various parameters that were used. But this is an easy way to start SimObserve. Just start up with the OST, run something there, get these parameters, and then you can start to play with SimObserve using this already set up. And then, of course, you can start tweaking. So you can try a different weighting scheme or have a different threshold for cleaning. Or that earlier on in SimObserve, you can try different map types, a different configuration, of course. Here it just picked one, but you can try another one. You can do a more compact configuration. This numbering goes from like 1 to, I think, 18 or more, from very compact to very extended. So you can try different things there, different thermal noise, etc., etc. Okay. So in the OST, in the iTrend session, there were already 3 demos. So I've actually used demo number 2 here. That's what I showed you before. But you could even start off with demo 1 or demo 3, and then run it in the OST, and then download these files, and then put it into SimObserve. So this is a quick way to get started playing with SimObserve and SimAnalyze. Okay. So much for the OST. Of course, in the second half of this presentation, we're going to go and play with SimObserve and SimData. There are some other tools available as well, especially from the Nordic node. Actually, there's a tool called, a task called FakeOps, which actually uses an observed data set where you can actually change things in there. So you can substitute visibilities in a particular data set with simulated visibilities from a model image, but using the same bandpass, same flux scale, etc. So you can keep bits, but also replace your data with a model image. So that's a nice deviation from just starting with a model. So here you're starting from actual real data. This can be downloaded from this GitHub here. And there's actually a basic CASA simulator as well for full polarization observations called PolSimulate, also from the Nordic arm. But that's for completeness. These tools are available. These tasks are available as well. Now we're going to move on to the CASA simulator in more detail. Most of everything you need to know is available online. CASA, of course, is mainly developed at NREO, so they have a large set of documentation pages on the simulator and everything else CASA, of course, as well. So we're just going to go to these pages after this short presentation. In fact, I'm going to go and do that now, I think, because I'm done with the presentation part. So this is the introduction. This was the introduction and the overview. Maybe there are already questions now on this part.
Yes, we have one question. Actually, what you mentioned. Hi, Olga, can you please elaborate a bit more? What you said that ALMA is not supposed to be run multiple times. What should be the recommended procedure? Okay. So multiple times means that, I mean, once it has run once, the project will actually be saved on disk, right? So you get these project files. It's probably best then, if you want to run it again, is to just remove that. So remove the previous simulation and run it again fresh, because it might keep bits from the last simulation, and then it might just keep on adding noise onto noise, for example. So it's probably best to just remove the actual data that was the mock data that was produced, and then just start it again. Okay, thank you. And Carmen has also raised.
I have a question myself. Sorry, because maybe I missed this, but can you repeat again, or what is the underlying reason for the differences in the noise estimated by the OST, and if you go directly to CASA?
Yep. So they both use the SM tool, but they use it in slightly different ways. So the OST wrote its own sim observe in a way, but with small differences. So they took some shortcuts to make it faster. And it's in the details. I really don't know what the actual details are, where it is actually different. But the way they handle things, the way to organize things, causes small differences in the noise maps.
Okay, thanks.
But they're both based on the SM tool, but just in a slightly different way.
Yeah, I see. Just that it's important, as you mentioned, to take into account, especially if you go to high frequencies, right?
Yep.
That you are, it's also difficult to simulate the noise, but yeah, I see. Thanks.
But typically the sources end up in the same place, right? There's not much difference in the actual sources. It's the noise map which has differences.
Yeah.
Okay, thank you. There are no more questions currently, so I think we can continue.
Yeah, so now we're going to the interactive mode. So I want to show you where all the documentation is. So these are CASA docs. That's just the documentation on the tasks themselves. Then the second part is the CASAguides. These are ready-made examples produced by the CASA team, and we can actually play with some of those. And then if we have time left, we can also go into batch processing of simulations if you want to do large numbers of them. Then it's just tedious to run them manually, of course. So you want to use all kinds of things to do it automatically. And this is fairly easy because CASA is basically based on Python. So it's just Python programming you can do to do batch processing. Okay, so let's go to CASA docs. If you go to CASA itself and the CASA docs page, then this is where you end up. On the left, we can see there's a simulations tab. So let's go there. And it's all explained, with all the warnings and tips. Now, I'm not going to read out all this. I'm just trying to show you where it all is and what can be done. There's something which they didn't talk about is this simutil. These are utilities which are also part of CASA, which you can use for various things. For example, here you can read antenna properties for an array, or I don't know how well this is documented. Yeah, this is very well documented. So people who want to really dig into the noise, for example, or want to understand the noise, simutil has various things to do that. It is basically just to point out that this exists, and this is where you can read up all about the tools and the tasks. This is the official CASA documentation, so this is fairly well maintained, I hope. But to actually get to know the simulator, of course, it's best to actually try it out. And here is where the CASAguides come into place. Let's go to the first page first. So if you go to CASAguides, this is just casaguides.nro.edu. You end up here, and there's various CASA tutorials on the telescopes, but on the right-hand side here, there's still the simulations one. And if you click on that, you get CASAguides on simulating observations. These pages have been there for a while, and they've also they still kept the ones for all the versions of CASA. Not the very old versions. There used to be a version for CASA 3 and 2 and 1. But they still keep the versions if people are still running 5.1 or 4.4 because they have old machines, for example, or actually like those better, then you can go there. It gives you a general introduction, but I've already done that. And then these are various tutorials. So one is on sim ALMA. and the other one is on SimObserve for a protoplanetary disk. Those are the two ones I would like to go into now. I was hoping that everything would still be available on these pages, but apparently some of the datasets which you're supposed to download are no longer available on the web. So I had to look them up myself, and I've now put those on the science portal. So if you go to the science portal to iTrain and iTrain number 15, there's now a link to scripts and data. These are fairly short files, which you can download. So you simply go here, and you can download these files. One is on M51 with the sky model, and the other one is a protoplanetary disk with the data set as well. In principle, it should all be here. And the CASA team made this script that extracts the CASA commands from this tutorial, because the tutorial has a lot of explanations and it has the CASA commands all mixed up. And there was a script that's supposed to extract those, but that doesn't seem to work very well. So I did this for you, and I put those on the science board. So this is the first one we can actually test. So I've got my window here. I'm actually using CASA 5.4, which is a slightly older version, because the next tutorial works on 5.4. But I've tested this before, and this ALMA tutorial also works on 5.4, so that's fine. One. But it's this fairly short set of parameters. I hope this is not too small to see, but you can download this file and open it up yourself. Of course, that's easier. So this is all you need for ALMA, all these files. So it gives you a project name. It gives you it tells you the sky model, which fits file to read, where to put it on the sky, and which antennas to use. Because I'm using CASA 5.4, the Cycle 8 antennas were not in there yet. The Cycle 8 configurations were not in there yet, so I'm using Cycle 7 ones, but that doesn't matter, it's just a demo. So if you run this, so the simple thing is to just use exec file. And what it actually does then is it does the 12-meter mock, the 7-meter mock, and the total power one. So it takes a little bit of time here because it's doing the three of them, and then combines all that. So it's good that this takes a bit of time, so you have time to download files if you from the science portal if you want. So it's now doing the imaging part. Now doing the imaging part for 7-meter. And now putting it all together. So these tutorials don't take too long. The idea, of course, is that you can then play with this and start changing parameters and see what happens. Okay, so it's done. So I'll make it a bit larger. So this is now the final simulation. The top left one is the input field. So you can see that we're not doing very well with this particular array configuration. We're not recovering much of the flux. We're losing a lot of the small dots. So it's fairly noisy. That's because this is probably a short integration. So here we can already see that we're not doing very well, and we probably need to integrate longer. So we can start playing with this, put in different integration times. So here the total time was just 1800 seconds. If you make that 18,000, then of course the simulation will take longer, right? So we can run it again, and then it will hopefully produce a better image. So while it's doing this will take longer, of course. Are people okay with downloading the datasets and the scripts? You could probably just open them up in your own editor. It's easier to read what's in them. And while it's running this, we can we can see what it's actually doing, and it's fairly well described in the CASAguides. So it explains all the various steps fairly well. So it's just also the CASA things. It sets ALMA as a current task. Then it specifies the sky model image. This is an H-alpha map of M51 from someone. I can't actually remember who produced this image. It's used a lot. You then set all the various, even though it's an H-alma image, of course, so you just pretend that the H-alma corresponds to the ALMA flux in this case at 330 gigahertz, so band 7. Which might not be the case, of course, but this is what you assume here. And then run this. So you set all things, the pixel size, and where it is. So you have to put it in the southern hemisphere, of course. That helps, otherwise you won't see it. And then you set up the observing parameters. So because it uses 12 meter and 7 meter here. This one is not actually using the total power configuration. It just uses the 12 meter and 7 meter. So the antenna list is now a vector. So you specify the 12 meter array and the 7 meter array. You can also add the total power one with another comma and then the total power configuration. And this one was set for 30 minutes. Oh, right. It actually does the total power. You just set it, the way it's done is that you just set the total power antennas. So if you set it to 2, then you have 2 total power antennas, which is fairly typical. And the integration time again, which should also be increased. I've increased the total time for the 12 meter and 7 meter, but not for the total power. So that's not going to do very well, I think. That would also have to be increased. So one good thing about the simulator is that you can actually set the amount of water vapor, so you can simulate what happens if the conditions are poor or when the conditions are good. So this helps, of course, to check how feasible your project is. And if you need really good conditions to be able to recover flux and all that, then you can put it in your proposal. You can say, well, I need really good weather for this. Or if not, then that helps, of course, to actually schedule it. Because it does sometimes take long, you can actually set driver to true and have a driver of the simulator. It will do a lot less work, but just to check what it actually runs. In the last part of this page, it actually explains what it's all doing. So all the nitty-gritty details are in. It actually doesn't change your input file. It makes a copy and then works on that. And here it tells you how it's actually doing the combination. So SimAlma by default uses feathering. This, of course, is not the only way of combining 12 meter, 7 meter and total power. So you can also do this yourself by hand. So if you want to do this manually, then there's some notes here on how to do this. just read that. It could be a bit dangerous to use this just out of the box and just use the defaults, right? So you always need to be careful that whatever you're doing, it makes sense. It's still running, right? Yeah, this will take a while. You can also see what it's actually doing on the sky. So the HCA map is actually a mosaic of this particular galaxy M51, and the same for the total power. So these are actually lots of pointings. This is a fairly expensive project if you would want to do it for real. And I think you can actually plot these as well, but you have to set that in the options. But I haven't tried that yet myself. I can try that here. Yeah, what's useful with these tasks is that you can also set graphics to both, which means that the graphics are put on the screen, but also to file. So all these graphics that are produced are also saved on disk. You don't need to do any screen grabbing or anything like that. Okay, and there were some improvements made for CASA 6 as well. So it now actually uses tclean instead of clean. As you know, probably tclean is now the default clean task in CASA. And there were some bugs in there which are fixed. But apparently you need to use CASA 6.1.1 because in 6.1.2 the bug fixes are not in them. I guess that's the pipeline version of CASA where the bug fixes were not put in. Don't ask me why. Okay, it's done now. Let's see if it's better. So this has improved. So 10 times integration time, the various knots of star formation now show up here. So we increased integration time, especially on the 12 meter and 7 meter part. And you can clearly see that the small scale structure is now much better visible. So this is a case where you can see that the simulator helps to see what the integration time should be to recover whatever you want to observe here, for example, the spiral arms. They're only resolved if you really go this deep. So that's one. The other example I wanted to show you was to just use SimObserve itself. So again, ALMA calls SimObserve and SimAnalyze. But if you want to use SimObserve yourself, or you want to do something like this yourself, then that will be the option to go for. And this is a protoplanetary disk example. There's also 5.4. This is the 5.1 version. I'm not doing the 5.4 version. 5.4, that's the one. So again, I've extracted the script for you because the extraction script didn't work. So all these commands are now in the file called psim2.py. This one, that you can download. This example is interesting because the FITS file that was used was not yet suitable to be used for SimObserve straight away. It needed some more keywords. Basically, it needed a coordinate system. So there are some CASA commands here to actually do that. So the first part of the script is actually just Python putting in the size of pixels and the size of the axes. In other words, the size of the image on the sky. And only then starts to run SimObserve. So it does a little bit of work to fix the image. What's also useful to know is the OST has a nice help page, the help documentation, and somewhere near the bottom, they clearly spell out what the FITS requirements are for the OST, but this also applies for the CASA simulator. So the FITS headers need to have these keywords. That's this whole list. So make sure that whatever FITS file you have has these keywords. What I usually do is use something like IDL or some other editor to add these manually myself, or whatever you want to use to work on FITS files. But it doesn't. The simulators do need these keywords, otherwise they can't guess how big your simulation is on the sky, of course. But this especially applies to theoretical models where you really need to make them more like an observation. So it needs the coordinate system, it needs pixel sizes, and that's what's here. And of course you want to rotate it as well. So it explains all that. Okay, so back to the example, Protoplanetary disk. This is much quicker. So if you want to really start playing with CASA, then just run the psim2.py version. Well, of course, I have too many windows on my screen. Yeah. But this is the Protoplanetary disk example. This is the top middle is the input file. No, that's not right. The input file is the bottom left, I think. And it does various analysis files. No, this is the one at the top in the middle is the input. So this is a Protoplanetary disk with something in there, a small source that actually is cleaning up this here. So this is someone's simulation. And this is what ALMA can then actually observe for this particular configuration. So what's useful here is that you can tweak parameters to see whether you can, for example, observe this source here, or whether you can actually resolve the ring. This is a fairly simple. So you could play with this a bit if you want. Let's see, what shall we change? Not the integration time, but maybe something else. So this is antenna list 20, which is a fairly extended configuration. But if we use number 2, for example, a fairly compact one, then it's going to look quite different. So the good thing about having these files open in your editors, you can simply change this. It's supposed to look quite different, but it doesn't. Interesting. Out2 should be quite a different set. For some reason, it's still doing out20.
I think Elko quickly sees that it cannot find this ALMA outdo config because you may not have exactly the file is not named. Perfect.
It might be out.2, O2, I guess. Yeah. It's probably O2, right? No, still does 20. Hold on. I have to change this as well, please. It was just running clean still on the old one. So sim analyze was running on the wrong simulation. There's so many parameters, you have to keep track of them all. So now it's cleaning the antenna 021. Yep. So nothing left. You sort of turn it into a point source almost. So this is a really compact configuration. So you see nothing. So this is maybe a bit too dramatic. So you can also try intermediate ones, of course, at 10 or 15, and see what would be optimal for your particular target. Yep. So one has to remember that one should also change the name of the file of the model image that was produced by SimObserve. Okay. So this was a short demonstration of what SimObserve and SimAnalyze can do. So this is probably the most dramatic disappearance of a protoplanetary disk. It just turns into a point source in a really compact configuration. You see nothing. There are some other examples here as well. I put on the science portal. This is another way of actually running. I don't know whether you can actually see this. Maybe I can. Is this at all visible, or is the font size too small? So of course you can exploit that CASA is written in Python, and you can do some Python programming inside of CASA and do, for example, loops. So here I have produced 2 for loops over lots of light cones for cosmological simulations. And I'm actually running 100 simulations automatically. So you don't need to do it this way by setting all the parameters and then type SimAnalyze or SimObserve. You can also just call SimObserve and have all these parameters in there. But this is another way of actually running it. And just put it in like this. And then you can use Python to insert things here. So for example, I run over parameter C and D, and I put together a file name for the sky model. So here on disk, I have sitting 10 different input models, 100 different theoretical images, which I'm then reading one by one and running SimObserve on, and also cleaning them. And then in the end, these are all analyzed and turned into fits files. A useful command here is export fits, which is another CASA task that turns an image, a CASA image, into a fits file. Because quite often source finders, and that's something I'm trying to test here, source finders need fits images as input and not CASA files, CASA images. So an export fits command like this is fairly typical at the end if you want to use a fits file. So this is just one example of how you can do things interactively in batch. The other example was a cluster, but this is not that interesting actually. So let's skip it. I think I wanted to include this to just show you how you can produce your own and have this export fits in there, but let's ignore that. So once you get used to running SimObserve and SimAnalyze, it's easy to include that into your own Python scripts and do things automatically. And then it becomes quite powerful. This, of course, is hard to do with the OST. If you want to do 100 simulations with the OST, then you have to do this manually by hand and submit this all the time. So with this kind of batch processing, you really should use the CASA tasks. And I think that's the end of my presentation, because there's still time for questions. We have about 5 minutes left. So any questions? Of course, feel free to email me if something was unclear or whether you want to do something different and want to get advice on how to actually go about it. So perhaps we can stop the recording and do the Q&A session.
We can do that. So